Hello. Today we're looking at probability distributions and expected value. It is St. Patrick's Day today. You guys are not watching this on St. Patrick's Day, but that is why I'm dressed in my green. So happy St. Patrick's Day for whenever you're watching this. Okay, so probability distributions and expected value. So to this point, we've learned a whole bunch of probability. Okay, lots of different basic rules, addition rule, multiplication rule, conditional probability, some miscellaneous probability, the binomial probability, the geometric probability. There's just tons of it, right? But as we saw, we were starting to get into kind of statistical problems with the geometric and the binomial probability. So we're going to take that a little bit further, and in this section we're going to take our probability distributions and probability and really turn them into statistical problems. Okay, kind of getting us towards where we're going. So a probability distribution distribution is a table that lists outcomes and their probability. So the definition is a little bit kind of goofy there, but basically a probability distribution is just a table. So what we're going to do is take our probabilities that we were learning in the last chapter and now turn them into kind of table form. So let's say that we're going to use an example we've used before. Let's say that we're going to roll one die, okay, just a single die. Roll die. Okay. So instead of listing the sample space and writing out the events, we're going to do this in a table form. So I'm going to let X be all the different outcomes that we could have, and then I'm going to put a column over here that's P of X. So we're going to have all of our different outcomes, and then we're going to have their probabilities. Now, like I said, we're rolling a die, which means this is kind of an easy one here, but our different outcomes would be 1 through 6. And because a die is fair, it means that each one of these guys is a 1/6. So, as I said, not the most exciting probability distribution, but it gets us what we want. We've got this in table form, we've got the outcomes, we've got the probabilities. Now, one thing to notice is the sum of all of these probabilities should always equal 1. So we can say the sum of the P of X should equal 1. And then we also want to note that these should always be positive and they should never be greater than 1. So these probabilities will always be between 0 and 1, each one of those. And this just falls back on our basic rules where we know that there are no negative probabilities and there's no probability over 1 or 100%. Okay, so it's basic rules here, but now you can check to make sure this adds up to 6 over 6, which is 1, and all of them are positive there. Now, along with a probability distribution goes a goofy little graph called a probability histogram. Now, I know we've looked at histograms before, but this one truly is just an easy little graph, okay, I promise. So the probability histogram just takes this table and it turns it into graph form. So what we're going to do is create what looks like a graph. We're going to have X, and we're going to have P of X over here. And then we're simply going to list our different outcomes. And normally, like we would, do a couple hash marks, like this would be 1/6, and this would be 2/6, and 3/6, and 4/6. But since all of ours have the same probability, this one's really boring. And instead of drawing bars like a normal histogram would, all we're going to do is draw lines. So each one of these has a probability of 1/6. So we're just going to draw a bunch of lines. And again, go with my graph. It should be perfect, but that's the way life goes. So there is our probability histogram. And the idea, again, is just that you have it in table form and you also have it in graph form. So you have both forms. Now, the thing here, like I said, is that what we're trying to do is get back into statistics. So by creating this probability histogram, what we're doing is relating this back to statistics. And we're going to use this to calculate different probabilities, and we're hopefully going to get this back. Like this graph would be considered uniform, right? But hopefully we're going to start seeing the bell-shaped curve again and all that kind of stuff. But before we do that, we want to talk about expected value. So, let's look at expected value. So expected value is the value that, I know it sounds dumb, the value that we are expecting, okay? But when we take probabilities into account. So expected value is the answer expected when probability is taken into account. So it's going to make a little more sense once we get our probability distribution on the board and we start working with it. But let's get the formula here first, and then we can get into the example. So the expected value formula is not a hard one. You can either label it expected value EV, okay, that's the way the mathematicians label it, or the statisticians label it mu sub x, okay, mu sub x. Whichever one you like better, expected value EV or mu sub x. Either way, the formula is not so bad. It's the sum of all the x times P of x. So let me give you an example here. I'm just going to put up a